Our universe's grand debut, the Big Bang, the universe. It's vast, it's mysterious, and it had a beginning. For decades we've called this beginning the Big Bang. Imagine all the energy, all the stuff of the cosmos, squeezed into a tiny, tiny point, smaller than an atom, hotter than anything you can imagine. This was the scene about 13.8 billion years ago. Then it started to expand. Not like an explosion in space, but space itself expanding. This is the Big Bang Theory. It's our leading explanation for how everything we see came to be. It tells a powerful story of cosmic origins, a story that scientists have pieced together with amazing evidence. Think about those first moments. It was a frenzy of activity. Pure energy transformed into particles. These particles then started to clump together. Protons and neutrons formed first, the building blocks of atomic nuclei. For a few 100,000 years, the universe was too hot for whole atoms to exist. It was like a super hot soup of particles and radiation. Light couldn't travel far, it just bounced around. But as the universe expanded, it cooled. This cooling was crucial. It allowed things to settle down, for structure to begin to emerge from the primordial chaos. This cooling process is a key part of the Big Bang narrative. Eventually things cooled enough for electrons to join with those protons and neutrons. This is when the first atoms formed, mostly hydrogen and helium. These are the simplest and most abundant elements in the cosmos. With atoms formed, light could finally travel freely. The universe became transparent. We can still see the afterglow of this moment. It's called the cosmic microwave background radiation. It's like a baby picture of the universe. This picture provides incredible support for the Big Bang model, showing us what things were like way back then. It's a snapshot from a very young cosmos. The Big Bang Theory successfully explains so much. It explains the expansion of the universe. It explains the cosmic microwave background. It even explains why there's so much hydrogen and helium out there. It's a cornerstone of modern cosmology. But, like all great scientific theories, it also raises new questions. Does it explain absolutely everything? What about the mysterious stuff we call dark matter? Did it also pop into existence during this fiery birth? Or does its story start even earlier? These are the questions that keep astronomers and physicists looking deeper into the cosmic puzzle. Whispers from before dark matter's older story. So, what is this dark matter? It's a cosmic enigma. We can't see it, it doesn't shine, it doesn't reflect light, it doesn't interact with ordinary matter in any significant way that we can detect directly. Yet, we are pretty sure it's out there. And there's a lot of it. Scientists estimate that dark matter makes up about 85% of all the matter in the universe. That means the stars, the planets, the gas clouds, you and me, all the stuff we see is just a small fraction of what's truly out there. It's a humbling thought, isn't it? How do we know it exists if we can't see it? We see its effects. Dark matter has gravity, and gravity pulls things. Astronomers first noticed something was off when they looked at galaxies. Stars at the edges of spinning galaxies were moving too fast, way too fast. If the only matter present was the visible stuff, these stars should have flown off into deep space. But they didn't. Something extra, something invisible, was providing the gravitational glue. That something is dark matter. It's like the unseen hand that keeps galaxies from flying apart. Its presence is inferred, but the evidence is strong. The standard picture for a long time was that dark matter, like ordinary matter, was created in the aftermath of the Big Bang. As the universe cooled, various exotic particles could have formed and then settled into the dark matter we detect today. These particles would have been born from the same primordial energy bath that cooked up protons and neutrons. This made sense. It fitted neatly into the Big Bang timeline. It suggested a common origin for all types of matter, both the seen and the unseen. This was the comfortable, accepted view for many years. However, some new ideas are bubbling up. Some scientists are asking a bold question. What if dark matter is older than the Big Bang? What if it didn't come from that initial hot, dense state we associate with the Big Bang? Could it be a relic from an even earlier epoch? This is a mind-bending concept. It challenges our traditional understanding of the beginning. It suggests that the event we call the Big Bang might not be the ultimate starting point. There might have been a before, and dark matter might have been part of it. This is where the story gets really interesting. Inflation's secret: how dark matter might have formed early. To understand how dark matter could be older than the Big Bang, we need to talk about something called cosmic inflation. Think of it as a prequel to the main Big Bang event. Most models of the early universe include this period. Inflation was an incredibly rapid expansion. The universe supposedly swelled up from subatomic size to something like the size of a grapefruit, almost instantaneously. This happened in a tiny fraction of a second, right before the hot Big Bang phase we usually think about. It smoothed out the universe and set the stage for everything that followed. What powered this incredible inflationary burst? Scientists theorize about something called the inflaton field, or inflaton particles. This field, or these particles, would have permeated the very early universe. They carried a huge amount of energy. This energy pushed space apart at an accelerating rate. It was a very different state of the universe than the hot soup of the Big Bang. It was a period of immense rapid stretching. The details of inflatons are still a big mystery, but their existence is a key part of making the overall Big Bang theory work with what we observe today. Now here comes the new idea, the Wi-Fi model. Wi-Fi stands for Weakly Interacting FIMP. A FIMP is a feebly interacting massive particle. This model proposes that dark matter particles weren't produced by the heat of the Big Bang. Instead, they were created during that earlier inflationary period. As the universe was stretching wildly, the very fabric of space-time could have jiggled enough to produce these dark matter particles. They weren't born from collisions in a hot soup, but from the dynamics of inflation itself. This is a radical departure from older theories. This creation happens through a process called freeze-in. Imagine the inflaton field is decaying, slowly transferring its energy to create other particles. Some of these particles could be dark matter. Because these dark matter particles interact so weakly, they barely noticed anything else. They didn't collide much. They didn't get destroyed. As the universe expanded and cooled, even during inflation's end, their numbers just got frozen in. They were produced, and then they mostly just stuck around becoming the dark matter we see today. This is a very different birth story than for ordinary matter. A new cosmic dawn, dark matter, the ancient messenger. If dark matter really formed during cosmic inflation, predating the main Big Bang inferno, it changes everything. It means the Big Bang wasn't the absolute beginning of all matter. It was a pivotal event, yes. It was the start of the universe as we know it, the beginning of atoms, stars, and galaxies. But it wasn't necessarily the creation point for everything. There was an earlier phase, a phase of cosmic inflation. And dark matter might be our most direct window into that incredibly early epoch. It makes the universe's story even grander and more complex. Our cosmic timeline gets a new chapter right at the start. Before the hot Big Bang, there was the inflationary era. This period shaped the universe on its largest scales. If dark matter originated then, it's been around for almost the entire history of space and time. It witnessed events that ordinary matter formed later did not. This makes dark matter not just some mysterious stuff, but a primordial relic, a messenger from a time before what we traditionally considered the beginning. It's like finding a fossil from an age we didn't even know existed. Think about what this means for discovery. Studying dark matter is already a huge quest. We build giant detectors deep underground. We use telescopes to map its gravitational effects. If dark matter is indeed older than the Big Bang, then these efforts gain even more significance. By understanding the properties of dark matter particles, we might learn about the inflaton field. We could get clues about the physics of inflation itself. This is something we know very little about. Dark matter could be the key to unlocking the secrets of that first tiny fraction of a second. So dark matter isn't just a puzzle about missing mass. It's potentially a direct link to the universe's birth pangs. It's a fundamental component of the cosmos that carries information from the inflationary era. It challenges us to think beyond the Big Bang as the sole origin point. The quest to understand dark matter is a quest to understand our deepest origins. It's a reminder that the universe always has more wonders to reveal, and we, as curious humans, get to be the detectives in this grand cosmic investigation. The universe is whispering its secrets, and dark matter might be one of its oldest storytellers.